Okay, this video is on molecular shapes. And first I'm going to ask you two questions. One is, are Lewis structures shapes? And second is, why do we even care about molecular shapes? All right, so are Lewis structures shapes? No, that's a big no. Okay, so when we draw the Lewis structure of water, it looks something like this. And when we draw it, it looks like it's all the atoms are in one line. But it's not a linear molecule. It's actually a bent molecule. So the shape is not given by the Lewis structure. Okay, why do we care about shapes? Shapes are extremely important in how a molecule acts. Biologists talk about enzymes catalyzing reactions in your body, and certain shapes are required in order for an enzyme to work. We can also look at water and say, what if water was linear? What if it was all in one line as a molecule? How would it be different than the way it really is, which its shape is bent? Okay, so if we had linear water in our world, we would have some problems. First of all the oxygen in the air, or most of the oxygen, would dissolve readily in the water. So there wouldn't be much left to breathe, because it would dissolve in the lakes and oceans. Secondly, we wouldn't really have lakes and rivers and oceans in the warm weather, because they would boil away. Okay, the boiling point for water would be lower if it were linear, so they'd boil away. And third, if we happened to have a cold enough day and did have ocean, it would contain no salt. Salt would not dissolve in water to any appreciable extent. Okay, so our life would be extremely different if water were linear. And that's supposed to convince you that shape is really, really important to explain properties of molecules. All right, so what does give us shape if it's not Lewis structures? Well, we use a theory called VSEPR theory, which stands for valence shell, electron, pair, repulsion. And I'll explain that. All right, and there are some steps for VSEPR theory. And the first one is draw a Lewis structure. So Lewis structures are the first step in finding out the shape of a molecule. Second step, count the number of electron groups, sometimes called charge clouds. So count the electron groups around the central atom. Okay, so what's an electron group? A lone pair of electrons is a group. A single bond is a group. A double bond is a group. And a triple bond is a group. So those are each one group. All right, so after you count the electron groups, you make electron group assignments. Make electron groups spread out as far apart as possible. The electrons repel each other, so they spread out as far as possible. And then the fourth step is look where the atoms are. Look where the atoms are to determine molecular shape. The molecular shape is not where the electrons are, it's where the atoms are. Whoops, do that one again. Look where atoms are for molecular shape. Okay, let's do some examples of this. First, we're going to do step 2, which was counting electron groups. You already know how to do Lewis structures, so that's step 1. All right, so let's count electron groups around a central atom. So we'll look at this compound, Antimony Tetrafluoride. You should be able to name that. And count the electron groups around it. We have a single bond there, a single bond there, a single bond there, and a single bond there. And I meant to say around the central atom. Count the electron groups around the central atom. Each of those things I circled is one electron group. So we have 5 electron groups. We have 4 single pairs, and we have 1 lone pair. So we have 4 single bonds and 1 lone pair. And that makes 5 electron groups. Look at this molecule, HCN, and look around the central atom. You'll see this is one group. A triple bond is one group. Single bond is one group. So it has 2 electron groups. Going further down, around the nitrogen, 1, 2, 3, 4. 4 E groups. And here's water. Around water, we have, around the oxygen in water, we have 1, 2, 3, 4. 4 electron groups. We'll do a couple more. Here on around the lead, 1, 2, 3. And around this carbon, we have 2. Okay, so hopefully now you can count electron groups. That is step 2. Then, step 3, make the electron groups repel as far as possible. All right, so let's do an example with 2 electron groups, which we just showed here. This last one we did had 2 electron groups. Okay, this one did. So we'll do an example like that and say we're going to draw things all as circles. Whether they're atoms or electrons, they'll be drawn as circles. So if you have 2 electron groups, and this is one group, and this is the other group, in order to get as far apart as possible around that central atom, they would get 180 degrees apart. And that would be linear. It's all in one line. And we say that that electron group geometry is linear. If you have 3 electron groups around a central atom, then the farthest they can get apart is 120 degrees. And that's all in one plane, and so it is called Trigonal Planar. It's all in one plane. All right, when we get to 4 electron groups, we're finally in 3-dimensional groups. 4 electron groups around a central atom. There's 1, 2, 3, 4. Those are in the shape of a tetrahedron, and we call it tetrahedral. And the bond angle between any 2, or not the bond angle, but the angle between any 2 is 109.5 degrees. All right, I'm going to show you a 3D, a little better picture of that. Okay, this one is tetrahedral. This is a sort of a more 3D looking model instead of my drawing of everything in a shape of a tetrahedron, and every angle there is 109.5 degrees. Okay, back to our drawings. If you have 5 electron groups, they spread out in this shape, which is known as Trigonal Bipyramid. And that's because it makes one pyramid on one half and another pyramid on the other half. I've colored these in shaded and non-shaded because there are actually 2 different angles in this structure. The ones that are shaded here are 120 degrees apart, and if you were to flip the molecule, it would actually look just like Trigonal Planar did. It's all in one plane, 120 degrees apart, except I've flipped the molecule. And then you have one that goes up, one that goes down, and the angle between the plane, this plane, and the up and down is 90 degrees. So we have 2 different angles in there. And I can show you a picture of that as well in a little more 3D model. Okay, so that would be this one. And so here you have your 3 planar positions, and you have one up and one down. And of course this can flip, but we're looking at it that way. This whole thing can flip and be in a different way, but it has 3 planar ones and 2 others that are at 90 degrees. Alright, so that's Trigonal Bipyramid, and the final one we're going to do has 6 electron groups. That is Octahedral. Okay, octa means 8, and it's 6 groups. The reason it's called octahedral is because these positions make the corners of an octahedron. Okay, so what we have is 6 different positions. 4 of them are in a plane. So you could say these 4 are in a plane in the page, or you can actually pick a different 4. You can pick the forward and back ones, and these little wedges mean that they're coming out of the page if it's on the wide end, and going back into the page on the narrow end. So there's one behind, one in front. You can also make a planar. You can make it planar from just using these 4 here. Okay, so that's an octahedron. I'll show you that one in a more 3D model, and that would be the one over here. So you have 4 in a plane either looking that way, or you could have 4 in a plane. You can choose 3 different combinations of a plane. Anyway, they're all 90 degrees. All the angles are 90 degrees between any 2 adjacent electron groups. Okay, so 90 degrees between any 2 adjacent ones. All right, so those are the different electron group shapes as they repel each other out. Now we're going to go through each category that I've listed here for electron geometries. Which is not yet shape. We have linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedral. We'll go through those one at a time. So we'll start with linear. Okay, that was too far. Whoa. All right. So linear. Linear is pretty simple. It's just example. I'll give you an example. Carbon dioxide. Okay, there's no additional electrons in the carbon because it has 2 double bonds. That makes an octet around the carbon. There's no additional electrons, so that's just 2 groups. So they spread out 180 degrees, and you have a linear molecule. Once you have 3 electron groups, you have the trigonal planar, and there are some examples which are exceptions to the octet rule. For instance, with boron trifluoride can be trigonal planar. Remember, it's all in one plane at 120 degrees apart. You can also achieve a trigonal planar electron group by having some multiple bonds. Okay, the nitrate anion, and I'm not drawing in the extra electrons. This is not a Lewis structure, it's a shape. Okay, so I'm not drawing in I'm drawing in the electrons around the central atom, but not around the outer ones. So there's some around the oxygens, there's some around the fluorines. We're only considering the central atom because that's the shape is relative to the central atom. Okay, so this one would also be 120 degrees. And that's because it's one of 3 resonance forms. So actually that double bond could be at this position, it could also be at this position, and the average is that it's spread out over all 3, so they're equivalent, and all the angles are 120 degrees. Alright, but we can also get trigonal planar electron groups with unequal positions. Okay, and this is formaldehyde. And so when they're unequal, when they're equal, your bond angles are going to be exactly they're going to be exactly 120 degrees. But when they're unequal, they will vary a little bit from the 120 degrees. So in reality, the bond angle here between oxygen and hydrogen is 122, and the bond angle between the two hydrogens is 116. So the 120 is exactly what it'll be if the groups are the same, but they'll vary from that if they're a little different. And how they will vary is that a double bond will repel these electrons a little more, so it'll make this gap bigger and this gap smaller. Okay, so we'll write that down. Double bond repels more. So we have unequal groups. Which means that the angles will vary from ideal angles. Okay, anytime they're unequal groups, they'll vary. All right, and you can have trigonal planar electron groups without having all the electron groups be bonds. Remember, they can also be lone pairs. So you can have this molecule, which would also have resonance structures with the double bond on each side, but it has a lone pair here, so it has 3 electron groups around the tin, and so it is trigonal planar electron geometry, but its molecular shape, unlike all these other 3 we just did, is not trigonal planar. It is called bent, because remember, the molecular shape is where the atoms are. The electrons determined that this would be in a trigonal planar electron geometry, but the molecular shape is bent. So that's kind of a subset of trigonal planar electron groups. Okay, so this is not trigonal planar. The shape is bent. All right, let's move on to tetrahedral, 4 electron groups. Okay, so remember in tetrahedral, the electron groups repel to a tetrahedron, and they are 9.5 degrees apart. And as long as the 4 groups are identical, which they are in methane, CH4, then they will be exactly 109.5. All right, and we can draw it like this. Remember, it's a 3D structure. We can also draw it like this with wedges, these 2 coming out of the page toward you, and this one going back behind. So there's a couple different ways to do it. You will do a lab that has you draw some of this. All right, so remember that the fat end of wedge comes out of the page. All right, so all angles are 109 degrees in methane. 109.5, correction. So that is the ideal bond angle for tetrahedral. But we'll see how some vary from that. Okay, so let's say that one of the 4 groups, unlike methane, one of the 4 groups is a lone pair. So we have a generic form with a central molecule A with a lone pair and 3 things bonded to it. For example, ammonia. Okay, a lone pair on top, 3 hydrogens. So this is still tetrahedral in the electron groups, but since one of the electron groups is electrons, the shape is not tetrahedral. The shape is called Trigonal Pyramid. Okay, so it makes a pyramid. If you think of this making a base of a pyramid, it looks like a pyramid. Okay, and so the angles will be less than 109.5 because the lone pair of electrons repels the other electrons in the bonds a little more. It repels more. So these the ones that bonded to hydrogen squish together a little bit, and your bond angle is not 109.5, but the bond angles between hydrogens are a little less than that. All right, but 2 groups can also be lone pairs. Okay, and here's the generic form. Some central atom A has 2 lone pairs of electrons and then 2 bonds. So it has 4 electron groups, but 2 are lone pairs, 2 are bonds. An example is water. Okay, and so I drew this more in the tetrahedral shape where this one would be going behind, this group would be behind, these two are forward, and this is also called bent. Remember we had a bent under Trigonal Planar, we also have a bent under tetrahedral electron groups, and here the angles will be less than 109.5 because the lone pairs repel more. Alright, so since we've been talking about angles, let's compare a few. These are the three we just did, and these were all for tetrahedral electron groups. Alright, so methane is ideal. All the electron groups are the same, all bonds to hydrogen. So those are 109.5 degrees, and they are ideal. They're the ideal bond angle. When you have one lone pair, they repel, that repels more. These bond angles shrink. This one is actually 107.3 degrees in ammonia. And in water, there's two lone pairs, so it shrinks even more. This one is actually 104.5 degrees. So they do vary from the ideal. So let's summarize again that electron pairs repel more than the bonds, which is why the bond angles shrink rather than expand. Okay, now let's compare, those were tetrahedral. Let's compare and look at the two different kinds of bent, because we said there was two kinds of bent shapes, one of which resulted from a tetrahedral electron geometry with 4 electron groups around oxygen. One resulted from a trigonal planar electron geometry with 3 groups. So we have 3 groups here, and here we have 4 groups, and yet both result in a bent molecular shape. Alright, and we already said that the bond angle here was 104.5. The bond angle, so this is varying from the 109.5. This one is now confined to a plane, so it's varying more. It actually shrinks to 95 degrees. Okay, so this one, the reason this one can be larger is that because it is in 3D space, it's in a tetrahedron, it can actually accommodate more electrons in the space. This one is planar, so they're confined to a plane, so that it shrinks even more. All right, let's have you try something. Try using VSEPR theory to predict the shapes of these molecules here. So stop the tape, figure it out. All right, let's do one by one. First, we'll count electron groups around the central atom. 1, 2, 3, 4. And I'll do this for all 3 of them. The second one, 2 electron groups. And the third one, 1, 2, 3. 3 electron groups. All right, so if you have 4 electron groups, the E group geometry for this one is tetrahedral for 4 groups. For this one, it's linear. And for this one, it's trigonal planar. Then you count how many of those are actually bonds, and this one has only 2 bonds out of tetrahedral, so it ends up as a bent molecule. This one has 2 groups. They spread out 180 degrees. They're both groups are bonds. So we have a linear shape, and I'm just drawing shape here. So that's linear. I'm not drawing the actual bonds, but I could, except I can't now. All right, and this one has 3 electron groups, but one of them is electrons, so only 2 of them are left over. So this one also turns out to be bent shape.